this and to explain in a little bit more details this analogy I started to present between a single quantum system with 1 degree of freedom at finite temperature and a statistical mechanical system, so a system of statistical mechanics, a classical system, but an extended one, a chain of various systems. So here is what I did. We started from a single quantum harmonic oscillator, and I showed you that if you are interested into the physics of this quantum oscillator at finite temperature, so the physics is described by quantities you can extract from the partition function, z, which depend on beta, but where beta is 1 over the temperature. Okay? So I did not TQ because it's a temperature associated to this quantum single object. So TQ will be the temperature for the quantum system. And we have seen that this partition function can be written as a path integral over some histories of the system, SQ, which are periodic in a time which is not the real time, but the Euclidean time. So we have trajectories, Q of t. They are periodic in this time variable, so Q of sigma has to be equal to Q of sigma plus tau, where tau is a period, and the period is given by h bar divided by the temperature of the system. And the weight associated to a given trajectory is simply 1 exponential of minus, please. No. The screen is there. Yeah, it's working because I have. Yeah, the screen is. Okay. Yes. And and the weight is exponential of minus 1 over h bar times the Euclidean action associated with the trajectory, where the Euclidean action is the integral over this time of the kinetic energy, if you want, plus the potential energy for this harmonic oscillator. Okay. So the idea behind the fact that to describe this path integral as a statistical system is just to discretize time, as has been done in the of the path integral formulation in real time. So we discretize time by introducing a small type step epsilon tau, which is very small. And so instead of having a continuous time, we have discrete time, piece of time, which has epsilon t times some integer I. Okay, and the number of such time steps is, of course, the total period divided by the time interval. And so this Euclidean action, written like that, simply, the derivative becomes a finite difference, q of sigma I minus q of sigma I plus 1 squared, divided by epsilon t squared. And there is an epsilon t, which is the volume element, the time element. So there is a 1 over epsilon t times this for the kinetic energy. And there is an epsilon t q of sigma I squared for the potential energy term. Okay? And now you still have this partition function. So here is what I draw, what this corresponds here. Oops, it's this. Okay? So we have a path integral where here we have the periodic time. The period is tau. We have this time step epsilon tau. And here is a typical path. So the particle is here at time 0. It's here at time 1. It's here at time 2, etc., etc. So in Euclidean time, it describes some trajectory. This is q, this is time. And simply, this trajectory has to be periodic. So once you are here, you are back at 0 time, and you start again your trajectory. And you sum over all possible trajectories, like that. Okay? And you have a weight associated to this trajectory. Okay? So the point is simply that you can describe the sum over such path integral, such path in Euclidean time, as simply as a statistical system in a chain of coupled classical oscillators. Because interpret this as the position of So you have a chain of oscillator along the you have oscillators along a chain. Okay, so this is the position we relabel tau x, the position along the chain. The time interval becomes a space interval epsilon x. Okay, yes? Pardon? No. I will just show you what it corresponds. We have a kinetic energy for this path integral. Simply now I relabel. I said instead of time, I call this the position along a chain. Instead of calling this a time interval, I call this a chain interval. Okay? Instead of the position q, I call it the value of an order parameter s at site E along the chain. Okay? And then I'm going to see what does this action corresponds to. Okay? So instead, so let me rewrite a dictionary. I have rewritten Q of sigma I Si, the value of the local order parameter at site S. So you can rewrite this Euclidean action as an energy which has simply the form. There is a term you sum over all the chain. You have a term which is proportional to the difference between the value of the parameter of the order parameter at two neighboring sites. And then you have this term which corresponds to the square of the value of the order parameter at a single site with two constants, K1 and K2, which are given by these terms for K1 and by these terms, so M omega 0 squared epsilon tau for K2. Okay? And now what I am doing is that instead of summing over Si, what I am computing, the partition function is given by something. So the partition function, you can either considering as an integral over dq of exponential of minus 1 over h bar Se of q. That's the quantum description, but you can also write it simply as an integral over a product of the site of dSi exponential of minus 1 over this E of Si. Okay? It's the same object, simply I have changed the name of the variables. Okay? And here you have something, some coefficient, which is h bar. But you can, of course, you can consider this as a partition function for a chain of oscillators. And so this is the energy. You sum over configuration. This is the Boltzmann factor. Boltzmann factor for the system at equilibrium. And therefore, the coefficient which is in the exponential is defined, in fact, as the temperature. So you can normalize it with a kBt. But here you have the equivalent temperature for this statistical system. So you see. So on one side, you have one single quantum harmonic oscillator here. But on this side, you consider that you have a chain. So this corresponds to a single quantum oscillator. And this is a chain of classical oscillator. Why is it a classical oscillator? Because you can view that when I write this, you can view this as the energy for a single oscillator, a classical. Pardon? That would be potential energy. But there is no kinetic energy because I am considering the equilibrium, the statistical mechanics at equilibrium. Okay. So I'm not, at the moment, interested into the dynamics of these classical systems. I'm not interested into how is it coupled to a thermal bath. What is the dynamics? From your statistical mechanical course, I think you have already seen that you have different kind of dynamics which gives the same equilibrium properties. You have Monte Carlo dynamics, you have Glauber dynamics for single spins. You have different dynamics which give the same equilibrium property. I don't care about that. I'm just interested in the properties at equilibrium. Therefore, I consider a configuration. It has a given energy, and that's it. Okay. So you see that you can view this as a term corresponding to the energy, the potential energy of a single oscillator, and K2 is just the spring constant for the single oscillator. So you have a collection of classical oscillator. Yes?
Sorry, with the K, because if you expand the first term out,
Yes?
that also be part of the K2?
Well, I choose to put it here. Okay, you can do what you want. Okay, but if I keep it that way, because that's the real, okay, you can see that this is a term which is proportional to the difference between SI, between the position of the oscillator at site I and the position of its neighboring oscillator at site I plus 1, with a different spring constant, K1, which is given by this term. Okay, M divided by epsilon tau. Yes?
So the periodic boundary conditions are something that can be somewhat arbitrary, right? The length of the period is given by the temperature that the quantum system is at, but the fact that there are periodic boundary conditions.
Oh, no. The fact that they are periodic, that must be periodic here, is because we are considering the trace of exponential minus beta h in the quantum systems. And the fact that we take the trace implies that we must consider periodic path. Yes?
Chain of oscillators, that's what we're saying. We are assuming that the vector displacements are small, so this line will be equal to delta y or something.
Okay, let me, in fact, there is no need to make any assumption because they are harmonic oscillators. So let me go back to this picture. So now you see that, oops. Yes. Now I have this, so I have those oscillators. Those oscillators can move only in the vertical direction. They cannot go like that. Okay, they move like that. Okay, and you have two springs. You have the springs here, which is proportional to, you have an energy associated to those red springs with a spring constant K1. I'm sorry, K2. K2 is a spring constant associated to the red springs. And K1 is a spring constant associated to the springs, the green springs. You see? And of course, the energy of a green springs is in fact proportional to 1/2 K2, K1, I'm sorry. In particular, it should be Si minus Si plus 1 square, if you are really. And then it must be also proportional to the distance plus epsilon squared. In this picture, if you think of it as real spring in a real two-dimensional space, and the spring can move in this direction. But this is a constant. Right? So the square of the distance between this point and these points is equal to this distance squared plus this distance squared. This is just Pythagoras theorem. And this is a constant, so I can forget about that. You see? Okay. So you see that this is the classical mechanical systems which correspond to this path integral for the quantum system. Okay? But now you see that the temperature of this classical chain of coupled classical operator is related to the Planck's constant of a quantum system, and the length of this chain of coupled classical oscillator is related to tau, where tau is proportional to the inverse of the temperature of the quantum systems. You see? So we have finally this dictionary that I started to describe last time, but I have summarized it here. Okay? On the left, we have the classical system at a given temperature Ts. Ts is the temperature of the statistical systems. And on the right, we have a quantum system, here a quantum oscillator, at a temperature Tq. Tq is the temperature associated to the quantum system. And we have this dictionary. Okay. Euclidean time for the quantum systems is the position, the coordinate along the chain for the classical systems. The elementary Euclidean time step you introduce when you discretize time becomes the elementary chain step epsilon x for the chain of oscillators. The position, the degrees of freedom of the quantum system, the position q becomes the local order parameter s for the spin for this classical oscillator chain. A trajectory, a given trajectory becomes a microstate, a configuration of these classical systems. Planck's constant for the quantum systems becomes the temperature of the statistical system. So quantum fluctuations here are related to the statistical thermal fluctuation of the statistical systems. And the inverse of the temperature of the quantum systems, namely the beta factor, the Boltzmann factor of the quantum systems, is related to the length, therefore the size, of the one-dimensional statistical systems. The Euclidean action for this trajectory becomes the energy of the microstate of the statistical systems. The weight associated to a trajectory in the path integral formulation, exponential of -1 over h bar times the Euclidean actions, becomes the Boltzmann factor associated to a given configuration, exponential of minus beta E of s. And if you work a little bit, in fact, you can go further in the analogy. And if you have already studied in statistical mechanics what is a transfer matrix, transfer matrix is an object which is very useful to study the property of the statistical system as you move along the chain. The analog of a transfer matrix is just the evolution operator along a unique step in Euclidean time. So there is an analogy between the evolution operator of the quantum system at Euclidean time and what is called the transfer matrix operator in statistical mechanics. And finally, these systems, it has a correlation length, usually, and the inverse of the correlation length is related to the mass gap or the energy difference between the vacuum state and the first excited state of the quantum systems. So this analogy goes along, you see? Okay, so I stop there for describing this dictionary between quantum mechanics of a single quantum system and statistical mechanics of an extended one-dimensional system. And I will go back to this analogy a little bit later when discussing quantum field theory and statistical mechanical systems in more than one dimension. Okay? So, are there any questions? Yes? Yes. Yeah, but yes, but you can do that in other way. You can change the energy of the system because it's equivalent to change the temperature and to change the constant. If you change the spring constant K, the same excitation costs less energy, so it's equivalent to consider the system at higher temperature. So you can play with the temperature by just playing with the parameter of the statistical system. Okay, but here it's a theoretical description, so we are free also to tune the Planck's constant. It's okay. Okay, so I will stop there for this presentation. And, oops, how is it working? So please, could you switch off the beamer? Thank you. Okay, so the second thing I asked, yes? You want an explanation? Well, the only explanation I can give you is that this mathematical derivation, it's a mathematical analog. You know, I show that there is some formula for the quantum system which are equivalent, so which gives the same results for other quantities calculated for an extended statistical system. And in this mapping, we see that the temperature of the quantum system is the inverse of the length. And I cannot say anything more at that stage. It's a mathematical analogy. And well, unless in some cases there is no really deep physical interpretation to that. It's a mathematical relation. Yes? Yes, yes. Yes, it's because the density matrix is given by exponential minus beta h, and this beta is the Euclidean time. So it's contained here. It's simply that beta is related to the Euclidean time. And therefore, it's the length of your path integral. It's the time during which you compute the path integral. Yes?
Do you also explain again how taking the trace gives the periodic boundary conditions?
Pardon, does?
How the trace, taking the trace.
Oh, that's, I explained that last time. That's simply because when I compute the trace of this operator, I can say that the trace is an integral over the position of the diagonal elements in the position basis. Those are position eigenstates of my harmonic oscillators. So states such that Q of Q times Q. So this is a state, this is a number, and this is an operator, the position operator. That's the standard formula for the trace. Simply expressed in the basis of position operator instead of an eigenstate, for instance, a basis of eigenstate of the Hamiltonian, but it's valid for any base. Okay? And this I can rewrite as a path integral for Q of sigma, such that Q of 0 equal Q, Q of tau and Q of tau equal Q is tau given by this famous relation, H bar KT. Okay? So the fact that it's periodic comes from the fact that we compute the trace. So that's very important. Okay? Okay. So, the second point I started to discuss last time was to discuss the relation between correlation functions in the statistical mechanical systems and the time order, the vacuum expectation value of time ordered products of two operators in the quantum system. So I went very, very fast, and in fact, I think that rather than doing the theory, I will just, at the end of this lecture, prove you by an explicit calculation that there is such a relation, because I will use, I know in English there is a famous proverb which says that the proof of the pudding is in the eating, and I will try to apply that. Of course, then we can do the math, but show you that it works, and then we can start to think again. Okay, so now let us start to do something non-trivial, which is to consider the quantization of the free field of the free scalar field by functional integral methods. Okay. So you have studied in the QFT1 lectures how you quantize a scalar free field, so real relativistic quantum systems, by the way of canonical quantization. So I will show you that one can do the same thing by using path integral methods. Okay? So what is a free field? At a classical level, a free field is a phi which is real and which is a function of the position in space-time. So phi is real field. And what I call x is a Kadri vector. So it's a vector which is given by a time component and a space component. And it belongs in Minkowski space. So let me denote Minkowski space by M of 1, 3. Or, in fact, M of 1 and d minus 1 in general, if I am interested into a d-dimensional space-time instead of a 4-dimensional space-time. And I will choose the normalization of time and space where the speed of light is 1, as usual, to simplify calculation. And here is the difference I already explained last time. I will choose as a distance between space-time events the distance in space coordinates. So I will use the matrix where this is what I call space-time, distance between space-time events. So I choose a metric with a signature which is minus, plus, plus, plus. So, okay. So now, and what is the action, the classical action for such a field, from which you can derive the Klein-Gordon equation and things like that? It's simply that to a field configuration, I associate a classical action, which is integral over d for x of 1/2. Well, this is the kinetic part of the action, the square of the time derivative of the field at any point of space-time. And then we have minus potential energy, which I wrote like that. So this is the minus 1/2 of the square of the gradient of the field at any point, and minus a term which is proportional to phi squared with the mass of the field. Okay? So this is the classical action, and from this you can derive the classical equation of motion of this classical field, which are the Klein-Gordon equation, in fact. Okay? Now, let us do the same thing and go into considering the Euclidean theory to make calculation simpler. So, to consider the theory at Euclidean time consists in doing a Wick rotation in time, but not while keeping space. Okay. So I have explained already briefly last time. It considers that instead of considering a vector in Minkowski space, I will consider now an Euclidean vector that I denote xe, okay, which will be, so I do the same trick that I did for the harmonic oscillator on quantum system. Okay, I decide that tau is it, so I make a Wick rotation, and this now belongs to, of course, Euclidean space. So this is R4 or Rd. I am in d dimension. Okay. So if I can make a picture, if I have some time to make a picture, see, here I have space. Here I have real time, and this is, I am drawing in a plane like that. Minkowski space. And what I am doing is that I am doing a Wick rotation to go from real time to imaginary time. This is a Wick rotation. So that now I am considering that instead of considering this Minkowski space, here I am considering Euclidean space. See? This is space, this is real time, this is imaginary time. Okay? So I make this transformation, and in this, with this transformation, of course, what is ds squared in the Euclidean region. This is, of course, d tau squared plus dx squared. So this is, we are dealing with a system in a matrix plus, plus, plus. So this is indeed Euclidean, the Euclidean plane. Okay, and now let us do the same trick. Now, what is the Euclidean action associated to a field configuration now phi of xe? So field configuration in Euclidean space-time. We know that this is, instead of being the integral over Minkowski over time of the kinetic part minus the potential part, the part which doesn't depend on time derivative, it will be the integral over both Euclidean time and space. So now we integrate over the whole Euclidean space-time, if you want, the whole plane, the whole space, Euclidean space, of 1/2 of d phi over d tau squared plus 1/2 of the gradient squared of phi plus m squared over 2 phi squared. Okay, so this is a form of the Euclidean action. Okay? Okay, so now we want to quantize the systems. Quantize this field. Okay? Yes? Pardon? Ah, sorry. Here, no, there is only plus sign. Why? Where? Sorry. Where? Yes. Yes, I signed both of them. Because this is, you see, okay, let us write it like that. This is the kinetic energy part. See, this term is a kinetic part, kinetic energy. And this term is a potential energy. Okay. So, when you go, in general, from quantum systems in real time to a quantum system where you have in Euclidean time, you keep that and you change the sign of the part which doesn't depend on the time derivative. You see? So we have to change both the sign here and the sign in front of this whole term. Is that clear? Pardon? Why? Well, I think it was clear. Okay. Pardon?
That's the definition. Last line.
Yeah, that's the definition. No, not only it's a definition, but it's simply, you can derive that by exactly applying the same rule that I did for a single quantum oscillator in last time. Because you can just make this change of variables here. So you define t equal minus I tau, and you assume that you make that with this definition, you have SE of phi equal minus I S of phi. So if you make this change of variable in S, and you redefine SE of phi as minus I, what you obtain in S of phi when you make this change of variables, then you get this. Okay? Okay. So, now, we want to quantize this field. So, the answer is quite easy because simply we expect that in order to quantize this field, we have to integrate over all the field configuration with some kind of measure on the space of field configuration on X with an exponential of, if I am in Euclidean time, minus 1 over h bar SE of phi. Okay, and this should give me the partition function of the quantum free field, just by applying what I did for a single quantum systems to a system with more degrees of freedom. You see? So, but what is exactly this partition function, in fact? One has to be a little bit more careful, in fact. You see, in this picture, you have to consider first that the field, instead of considering space equal to R3, I will consider that space is a box of size L times L times L with periodic boundary conditions. Okay, so I consider that the space on which my field lives is a torus. Okay, that's for simplicity. Okay, so here is the space. The space is a box like that. Here I draw it in 2 dimensions instead of 3 dimensions, and I assume that I have periodic boundary condition, and my field lives in this space. Okay. The second thing that I'm going to do is that I'm considering this field, the free field, this free field, considered as a quantum system. I consider it at finite temperature. Okay? Simply because it's simpler. So, the field is at a finite temperature that I will call TQ. TQ because the temperature associated to this quantum system. And therefore, that I know that then if I compute the partition function Z, where Z is simply the trace of exponential minus beta h, where beta is, as usual, 1 over kb times the temperature of the quantum field, and h is the Hamiltonian of the free field. I have not computed the Hamiltonian. I simply assume that there is a quantum operator acting on the Fock space, the Hilbert space of all the states of this of the free field. So there is an Hamiltonian. The partition is given. The function partition is like that, and this is a trace over the huge Fock space of all states of the free field. Okay. But okay, so I'm interested in computing this partition function for a system with many, many degrees of freedom, a field living in a box at finite temperature. And if I'm considering a field at finite temperature, I know that what I have to do is that to integrate over periodic Euclidean time with a period tau, which is, as usual, h bar over kbt. So, yes?
Is this a classical system that you
No. I am considering a quantum system. So I am considering a quantum field in a box, yes, with periodic boundary condition because it's simpler, simply. We can do it, of course. You may consider a quantum system is in a box with a fancy boundary condition. I consider it periodic boundary condition simply because it's the simplest case where you compute. Yes?
So does the conversation of your field now depend on the temperature that it's at?
No. I'm considering quantum system, and simply I'm interested in computing some properties of these systems at finite temperature as a first step because it's simpler. And then, for instance, I will take the 0 temperature limit because then I am projected on the vacuum state of the field. Okay, so it's simply a step to do the calculation knowing that everything is finite. Okay? So, instead of calling this period tau, I will call it this L tau, simply. Because you see that time here is just one one component of real space-time. So this period, I call it L tau instead of tau. So this is the size of the system in the time direction, in the Euclidean time direction. And so if I'm considering this free field at finite temperature, so finite space plus finite non-zero positive temperature, okay, my space-time, my Euclidean space-time, I have to consider space-time is now a torus in the time direction with size L tau. Okay, so it's a box if you want. It's a box with size L tau in the first direction, which is the Euclidean time direction, then L times L times L in the space direction with periodic boundary condition here. Here, that's because I am at temperature TQ, which is positive, and here it's because I'm considering that space is a torus, if you want, for simplicity. So you see the fact that I'm considering that time is periodic and that space is periodic comes from two different objects. Here, that's because I'm considering the free field, the quantum system, at finite temperature. And here, that's because I have chosen, for simplicity, that my space, the real space, is also periodic. Okay? You see? So, here I have a formula which seems a bit formal, which is then I am integrating. So space-time is like that. So space-time is a box, if you want. I can draw it like that. I will erase that. And space-time is now what is my space-time? I have my space, which is like that. This is space. Here I have in 2 dimensions. Okay? So I have periodic boundary condition. And here is time. Okay? So, sorry, that's a bit strange. So this is space. This is time. So you see? So here I am space in 2 dimensions. So for instance, if I was in two space dimension and 1 time dimension, my space-time would be a 3-dimensional box with a size L tau and periodic boundary condition in the time direction. And it will be a box with size L times L in the space dimension. So my space-time is a torus. You see? And now I am integrating over all possible field configuration in this space-time, in this torus. You see? Okay. 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 And oops, here it is. So I hope that we have kept this formula, and also now this action I can rewrite it in a way. This Euclidean action, in fact, I can simply rewrite it in a covariant way as 1/2 of d phi over dx mu d phi over dx mu plus m squared over 2 phi squared, where x mu are the components two, 3 of my Euclidean space-time. Okay, and with periodic boundary condition. Okay. So if I know how to compute this object, I know how to compute quantities in a non-trivial, well, simple, but because it's a free theory, but already a fully fledged quantum field theory. Okay? So in particular, now I can consider, for instance, take a point x1 in my Euclidean space-time, point another space-time point in my point, and I can consider the expectation value of the products of operator at 2 points in my Euclidean space-time, which will be defined, for instance, simply by definition, as a functional integral over d phi of this exponential of minus 1 over h bar SE of phi, okay, times phi of x1, phi of x2. And I normalize so that the expectation value of this is 1. So I normalize this by the partition function, exponential minus 1 over h bar SC of phi. So you can take this as a definition of an expectation value of a product of 2 fields at 2 space-time points x1 and x2, okay, and expectation value over which state? Over a thermal state. The thermal states defined by this temperature Tq, okay, and in space, in this space, okay. And if I know how to compute this in Euclidean space-time, I expect, and if I have time, or at the beginning of next lecture, I will show you that I expect that if I start from position where I expect that going from x, E in RD into x in Minkowski space, by weak rotation, I expect that I will recover expectation value of time-ordered products of 2 operators in the same state. Okay? So now let us see how we can is it very complicated, or is it easy to compute such an integral, and in particular, is it easy or complicated to compute such an object? The object which is defined here as the expectation value of the products of these 2 fields given this weight. Okay? And in fact, it's very, very easy to compute this object in this formalism. This formalism is very abstract. I have not really defined what is this functional integral. If you want to do some serious math, you have to work in order to define what is this measure, how you can define that. But as far as calculation of some quantities are concerned, once you know that this integral makes sense, and believe the mathematicians, they know that it can be built, you can compute very easily a lot of quantities. Why? It's easy to compute things. Easy because this is a Gaussian integral. And you have already met Gaussian integrals in a simple case, especially in the tutorials of yesterday afternoon. And I will just apply standard results about Gaussian integrals, or if you want language of probability, Gaussian random variables, to this case. Okay, so what is the difference is simply that here, okay, so I have written the action, I have written what I want to compute, and now let us consider at the mathematical level what I am considering. Okay, let me call this space-time X, simply. X is a torus with size L tau times L times L times L, okay, with an Euclidean metric. So it's an Euclidean metric in it, okay, and so the space I am integrating over what? Over a space of function. So let me consider, well, instead of X, because it's a bad definition, because X is a point, so let us call it M. It's some kind of very simple manifold in math. It's a torus, a flat torus. Okay, so phi, the phi of X, in fact, the function phi are functions. The function phi which to a point X in M associate a number phi of X in R, in a real number. In fact, the functions phi are just elements of a space of functions from M to R. And let me denote this space of function E of M. So E of M is a space of function phi from M to R. Okay? So I will not specify at that stage exactly what is this space. Are those functions regular one, continuous or non-continuous? It's just a space of function, and in fact it's a vector space because you can. It's a vector space because you can add function and multiply them by a real number. So it's a vector space. Okay? And what is this action S of phi that I brought here? S of phi, SE of phi, okay? You may consider it as is an application, so function if you want. It's a function from E of M onto the real number, which to a function phi associates the value of the action for this function. So it's a function from a space of function into the real. So it's just another function, but a function from a much bigger space, the space of a function of a space-time onto the real. So it is called, it's a mathematical literature, a functional. Okay, it's a functional because it's a function from a space of functions into the real. Okay? And remember that M is a torus. So we have periodic boundary conditions. And the action is given by this formula. So it's easy to rewrite. You can rewrite SE of phi by integrating by part the function. I assume that the function has some differentiability properties. And it's easy. I can rewrite the action as, first I can rewrite the action as SE of phi. Because I have boundary condition, I can rewrite it as d4x over my space M, my torus, of phi of x times a differential operator which is minus the Laplace-Beltrami operator of a space-time minus delta of x plus m squared times phi of x. Okay, there is a factor 1/2, of course, and delta of x is just the sum over mu of d over x mu, d over dx mu, and it's called the Laplace-Beltrami operator acting on scalar functions. So mu goes from 0 to 3. I'm in a 4-dimensional space-time. Okay, so it's simple integration by parts leads from this to this. Okay? Now I will do one more step, I will rewrite this as 1/2 of, and I will write this as a double integral d4x1, d4x2 over space-time of phi of x1, phi of x2 times some function of x1 and x2. Okay? And what is this function? This function, d of x1 and x2, is simply minus the derivative with respect to the mu component of the first variable x1, the partial derivative with respect to the mu component of the second component. I am summing, of course, over 3, so and plus m squared. Okay, and this is applied. So this is another differential operator, and I applied it to not exactly a function, but a distribution, which is a Dirac distribution of x1 minus x2. Okay. Okay. So you can easily go from this expression to this expression, because you can easily integrate over x1. Use derivative and integration by part rules over the delta function. At the end, of course, since there is a delta function, you end up with this expression. Okay? So you can always rewrite the action as a double integral over the function at the point x1 times the function at the point x2 times some function of the 2 points x1 and x2. And of course, this is not really a function, it's a distribution. Okay, so it's a distribution. This is object. Distribution in the sense of mathematicians, because here I have the Dirac distribution. Okay. But what is this this object, this d of x1, x2? In fact, it is called simply, so this function d of x1 and x2 is called the kernel, or in fact the integral kernel of the operator minus Laplacian plus m squared. Okay? Why is it called the kernel? It's because, let me write this this differential operator minus Laplacian plus m squared, capital D. Okay? Why is it called the kernel? It's simply because this is an operator acting on functions. So you may consider, what is this operator? I take a function phi of x, and then I want to compute what is the function which is minus the Laplacian plus m squared applied to this function. So it's I have a differential operator acting on a function, and I want to compute the value of this function at any point. And you can easily check that you can rewrite this as an integral over the whole space-time, here my torus, of this kernel, x and y, times phi of y. You see? And exercise, take this function, which is in fact a distribution, multiply it by phi of y, integrate over y, and with a little bit of integration by part, you reduce to delta function, and you obtain that this object is simply, indeed, what we wanted. So it's simply minus Laplacian of x plus m squared applied to a function phi of x. Okay? Okay? So in some sense, in fact, this is an operator, and this function represents just the matrix element of this operator acting on the space of function. You see? So this is like the matrix element. Okay? Because it's very, very similar to the fact that, so it's very similar to the fact that if you have vectors in an integral space, if you have a vector v, which is vi, I equal 1 to n in Rn, and if you have an operator A, an operator A acting on V, A of V I, the component I can be written as AIG, sum over G of AIG Vj, where AIG are the components of the matrix which represents the operator A. Okay? So this is a formula which is very similar to this one. So this is a formula which tells you how an operator acts on vectors in a vector space. And this is a formula which tells you how this operator acts on a vector space, which is the vector space of functions from M to R. Okay? Okay. So now, what are the properties of this differential operator? First, you see from this formula that this is a symmetric operator, if you want. It's a symmetric in x and y, x1 and x2. You can exchange x1 and x2. So it's a symmetric matrix. Okay. Now, you can realize that the Euclidean action I wrote before is, you can write it as simply as d4x. So that's what I wrote here. You can write it as, in fact, a quadratic form. You can write it as phi d phi. I'm rewriting this like that. So the Euclidean action is, in fact, a quadratic form on the space of function E of M. Okay? It's in fact 1/2, sorry, 1/2 of phi d phi. You see? And that's analogous to the fact that, in general, if I have an operator like that, I can consider the quadratic form V AV, which is sum over IG of VI AIG VG. You see, it's exactly the same. Okay? So in the same sense, in fact, you can view dxy as the matrix elements of the operator D, and the action as the quadratic form associated to this integral kernel. You see? Okay? And now, with that, we are almost done, in fact, because we are interested in computing. We were interested in computing, so let me use this blackboard. I was interested in computing the expectation value of phi of x1, phi of x2, okay, with a weight which was proportional to the exponential of minus this quadratic form. So I can write it as so the point is that the phi of x is a Gaussian, a set of Gaussian random variables with a weight, probability weight, P of phi, which is simply exponential of minus 1 over h bar, 1 over 2 times, well, I think it's SE of phi, so it's, no, I'm sorry, so this is 1/2 phi d phi. Okay? So I have the probability weight associated to this random variable. This is just the exponential of minus some quadratic form. You see? So it's analogous to what you have computed yesterday. Simply for this integral kernel instead of a single matrix. Okay? And therefore, we know that this object has to be equal to the variance of this probability distribution. Okay? Because you have seen that if you have a vector, if you have a vector which is, if you have a vector vi, which is a Gaussian random variable with probability weight P of v equal exponential minus 1/2 of v AV, we have seen that the expectation value of vi Vg is simply the matrix element Ig of the inverse operator, the inverse matrix RIA. Okay, that's very standard results of Gaussian integration. You see? So we deduce from that we expect that this object, this quantity, phi of x1, phi of x2, will be simply the integral kernel of the inverse operator d minus 1, the inverse of this operator. And let me denote this object. Well, there is a h bar, so in fact it will be this times h bar. So in fact it will be equal to h bar times an object that I call g of x1, x2, where g of x1, x2 is simply the integral kernel of the inverse operator d minus 1. That I denote like that, d minus 1 of x1 is 2. Okay? But what does it mean? So now we just have to understand what does it mean, what is the integral kernel of this inverse of this operator. You see? And in order to understand what is the inverse, we just have to understand what is the multiplication of operators, of such operator acting and function. Okay? And I see, well, we started a bit late, so I think so the question is, what is multiplication of operators acting on functions? Okay? Let me consider two operators. I have an operator A, which is represented by a kernel A of x1, x2. And an operator B, which is represented by a kernel B. Well, this is an operator, so it's curly. And this is a kernel, so I prefer to use Roman letters. Okay? So this is a kernel associated to the operator A and operator B. And we may ask, what is the kernel of the operator A times B? So I multiply the operator B by the operator A. This operator has a kernel. Let us call it C of xy, or x1, x2. Okay? What is this kernel? Well, it's easy. It's to realize that it's just the integral over some intermediate point of B of x1, of A of x1 y times B of y x2. Okay, so this is the kernel of the product operator, and it's given by this convolution of the two kernels. And it's just the generalization to operator, to kernel, to integral kernels of the law of multiplication of matrices. You see? Okay, and now I will. This operator d minus 1 has the properties, of course, that d applied to the operator d minus 1 has to be equal to the identity operator. That's the definition of the inverse of an operator. What is the kernel of the identity? Okay, so the kernel of the identity, I of x1 is x2, is of course the Dirac distribution of x1 and x2. You can verify it very easily that when you multiply this integral kernel by any function in this formula, you get the same integral kernel. That's the definition of the delta function. So this is the kernel of the identity operator is the Dirac distribution. Okay? So now let me apply this, rewrite this in terms of internal kernel. What is the integral kernel of D, this operator? We computed it before. And we are looking for the integral kernel of this operator, namely we are looking for the integral kernel of this G. So this, in terms of kernels, gives a very simple equation. It gives the equation that minus Laplacian plus m squared, the differential operator we started from, minus the Laplace Beltrami operator plus m squared, applied to the integral kernel of the inverse of this operator we are looking for, has to be equal to the integral kernel of the identity. Therefore, it has to be equal to a delta function in 4-dimensional space-time of x1 of x minus y. Okay? Yes?
Sorry, which stage is going to be?
Pardon?
The middle block.
Yeah?
The very last stage. Is that the same as this inverse up here?
Yes. By definition, I'm defining G as the integral kernel of this operator. So it's, if you want, by definition, I have to find what is the integral kernel. Integral kernel of the operator d minus 1. You see? And I see this operator d minus 1 is defined by this equation. So I rewrite this equation using this interval convolution of integral kernels. But the integral kernel of the operator d, which is a differential operator, is simply a differential operator applied to a delta function. So if you do the calculation, you end up simply by this differential operator applied on the integral kernel of its inverse that we are looking for, is given by the integral kernel of the identity, which is a delta function. So we end up with this equation, okay, which is an elliptic partial differential equation. Very, very well known. Okay? And now, up to now, I have not specified at all in which space I am. So, in principle, you have to solve this elliptic partial differential equation on the space M, which is M, which is the torus. Okay? So now, instead of looking at M being a torus of size L by L by L, I will go directly into the limit, because it's simpler, where L2 is equal to infinity. So I am at 0 temperature, and therefore I am computing I'm projecting into the vacuum state omega of the quantum theory, and I will also take the limit from the size of space, so I have an infinite space back. Because it's simply, I can solve this equation in any finite dimensional space-time, but it's simpler to write it in a finite dimensional space. And I think you give me still 2 minutes. Okay. I want to solve this equation. To solve this equation, the best way is to go to Fourier transform by writing that first this function g of x and y is a function simply of g of x minus y, because this equation is invariant by translation. And I can define this function of z as the integral of t for k 2 pi to the power 4 exponential of I k times x times its Fourier transform. Okay, and this equation becomes then, let us write it here. If you do the Fourier transform of this equation, it's very easy to see that the Fourier transform of the delta function is 1 on one side. And here I have the Fourier transform g hat of k. K is a four-dimensional vector. And the Fourier transform of this differential operator is simply k squared plus m squared. K is a vector, and this is a scalar product, so k squared is simply a sum over mu, from 0 to 3, k mu. Okay, so it's a scalar, so it's the norm, the square norm of the vector, and therefore g hat of k equals 1 over k squared plus m squared, and therefore we have computed this finally simply by doing Gaussian integration into h bar times integral into Fourier transform in 4 dimensions of exponential of I times k times x times 1 over k squared plus m squared, which is the final results I wanted to obtain. Okay? And you see, we have obtained this result simply basically by doing Gaussian integration. Okay? So it's a very easy. And this object is supposed to be, in fact, from that we are expected to recover expectation value in a quantum theory of products of operators, of local field operators, which are slightly more complicated to compute using canonical quantization. Yes?
Is there a minus in the exponential in that expression?
I will take in my lecture the definition, which is the definition by mathematician of the Fourier transform, which is the Fourier transform of the function x is integral dx exponential minus I kx f of x, and therefore the inverse Fourier transform is integral dx over 2 pi if I have in one dimension, so dk e to the I kx f k. Okay? So that's, I'm afraid it's also the opposite one definition that the definition in Peskin books. But it's just, it's just a definition. Here, in fact, here it's not important because you can change k into minus k. This is invariant on a Channel thing, and the measure here, since we are in an even number of dimensions, well, no, even in the other case, it's so in fact, you can change k into minus k, it doesn't change. It's just parity invariant. Okay? Yes, you have another question?
I was going to say, maybe tomorrow we can talk about rotating it back to real space.
Yes, that's, well, of course, the last thing we have to do. Now, we have to, this is an expectation value in Euclidean space-time. So we have space, three-dimensional space, and Euclidean time. So the last thing we have to do is to go back by a Wick rotation into real time and check whether we recover the same object that the one you computed in the first quantum field theory course. This will be the crucial and definite test which tells you whether this quantization by functional integral makes sense, functional integral method makes sense, or whether it's complete crap. Okay? Pardon? Oh yes, of course. I'm sorry. X is equal to x1 minus x2. Of course. Yes?
Okay, so this is an expectation value on the vacuum because you took that unit.
Yes, in fact, I expect, well, I was a bit short, but I expect that this is the expectation value of those products of operator in a thermal state at 0 temperature, and the thermal state at 0 temperature is the vacuum state of the theory, because it's the lowest energy state. But we are still here in Euclidean space-time. So we are still in Euclidean time plus space. So we have one last step to do. If we believe that all those receipts I gave you work, to check that we got the right result. Okay. But I will do that tomorrow morning. Thank you. Yes?